This is problem 3. And now we will consider a spherical shell with inner radius A and outer radius B. And this spherical shell is conducting spherical shell. This spherical shell, so the metal is right here. This is spherical shell conducting. And this spherical shell is charged with charge Q. And as we know, if we charge metal, the charge is on the surface. So this spherical shell is charged with a given charge Q. We are looking for electric field everywhere. Find the electric field everywhere. We will use Gauss's law to solve this problem that tells us that flux of the electric field E dot ds through closed surface is equal to charge enclosed by this surface divided by epsilon naught. The first area that we will consider will be R less than A. R less than A, we are inside spherical shell. We need to draw Gaussian surface. And since we have spherical symmetry, our Gaussian surface will be a sphere. This is imaginary sphere, not exactly sphere, but close. So this is imaginary sphere, Gaussian surface, and radius of this sphere is arbitrary r. This r is less than A. Now, from symmetry, we understand that electric field is in radial direction. ds for this sphere is also in radial direction, perpendicular to the surface. So E dot ds is just integral. E dot ds is just integral E times ds. Now from symmetry we understand that electric field is the same at each point of this imaginary sphere. I take E out of integral, it's constant, and integral ds is area of this sphere, which is 4 pi, and radius of our sphere is arbitrary r. E times 4 pi r squared is the left hand side of Gauss's law. It is equal to Q enclosed, no charge enclosed by this surface, so the right hand side is 0. And from this we immediately see that electric field in all this area for r less than A is 0. The second area that we will consider will be r greater than A and less than B. Now we are inside this spherical shell. But what is the electric field? We are right here between A and B. What is electric field inside the metal? Electric field is 0. We are inside this conducting shell. Electric field in metal in a conductor is 0 in electrostatics. Now for the third region that we will consider will be R greater than B. Now our Gaussian surface will be in this area. This is again a sphere, imaginary sphere for any arbitrary r that is greater than B. The left-hand side of Gauss's law from symmetry, we understand that electric field is in radial direction, ds is in radial direction, dot product E dot ds is just E times ds. E is the same at each point of this Gaussian surface. We understand it from symmetry. There is no special direction. So again, I can take electric field out of this integral. So the left-hand side of Gauss's law will look the same. It is E that we are looking for times 4 pi r squared, area of our imaginary sphere. And this is equal to charge enclosed over epsilon naught. Charge enclosed by this surface is Q. So I put it equal to Q, and we don't forget epsilon naught. So what is the electric field? Electric field outside of the spherical shell is Q 1 over 4 pi epsilon naught Q over r squared, and the direction is radially out. So either I put here radially out, or we will just put unit vector in radial direction. So from outside of this spherical shell charged with charge Q, we have the same electric field as electric field created by a point charge located at the origin. From outside, we cannot say what is there, either spherical shell charged with charge Q or just point charge. The solution looks the same. So what we did, we found the electric field in all these regions. For r less than a, for r between a and b, inside conductor electric field is 0, and for r greater than b, electric field looks like electric field from a point charge.